Okay, now I'm going to talk about blood typing and how it relates to paternity testing. Blood typing is a very old method of paternity testing. And it's an old method because it was very simple to use. The problem with it is it's not entirely accurate in all cases. That is, it can sometimes prove a person is not the father of the child. It can never prove 100% that a person is the father of the child. And we'll see that illustrated with our examples. However, sometimes it can, as we could say, exonerate someone from being the father. So there's a certain procedure we use to do this. Basically, we're going to know the blood types of everyone involved, but we're going to know their phenotypes, and we may not know their genotypes exactly. After we find out the child's blood type, then we know that the child must have gotten one allele from his father, one allele from his mother. So we're going to first try to find out what the allele the child got from his mother, and then that second allele is the one the child got from his father. So we're going to try to track down the source of that second allele. Let's look at our first example. Okay, we have a mother who's type A and a child who's type B. In the very beginning, I put an underscore because I'm not yet sure what that second allele is. This mother may be AA or BB. So let's look at the child. The child is type B blood. Okay, the child must have gotten the B allele from one parent, and the child must have gotten another allele from this parent. Right now, we're not sure whether it's the child's BB or BO. So let's look and see if we can find that out. The child's mother is type A, so she must be AA or AO, but we can look at it. She did not give an A allele to the child, right? Or the child would be AB. That means the mother's genotype must be AO. The mother's genotype is AO. The child's genotype must be BO, right? Because the child must have gotten the O from the mom, and where'd that B come from? The dad. So we're looking for the source of the B. Okay, this man, he has an A allele, he's got a B allele. He could be the father. He could have given this B to the child. Okay, so this man is a potential father. And let's look at the second man. This man has an A allele. We're not sure what that other allele is, but he does not have a B allele to give the child, so this man cannot be the father. Only a man with a B allele could be the father of this child. Okay, now, once again, the fact that this man could be the father does not prove there's not a third man out here who is the real father. So that's a limitation of blood typing as paternity. Let's go to our second example. Okay, we've got mom, type B, child's type O. Now remember, O is recessive, so the child's genotype must be OO. He has no A, he has no B. That means the child got an O from both parents. Mom's type B, she's got to be BO, right? Because she had to have an O to give her child. Okay, so we know the child, we know the mom. Now we're looking for a dad who has an O allele. Now let's look at this man. He's type B blood, but if he is homozygous B, that is BB, he's not the dad. But we have no way of knowing that. So this man, he could be the dad. If he's BO, he could be the dad. Let's go to the second guy. He's type A. Once again, we don't know if he is homozygous, that is AA, or we don't know if he's AO. So this man could be the dad. If he's AO, he could have an O to give the child. Once again, we can't prove which of the man is the father, and all we can say is both of them could be the father. Once again, we can't say there's not a third man out here who is the real dad. All we can say is we can't rule either of those guys out. Okay, let's look at our next example. Alright, we've got a child. We know the child's genotype for sure. He's AB. He's got an A allele from one parent and a B allele from the other. We've got a mom. She's also AB. So we don't know if this mom gave the A. We don't know if this mom gave the B. She could have given either one. We're not sure which one of those she gave. So we're looking for a dad who has either an A or a B. Any dad with an A or a B is a potential candidate. So this guy, he is type B blood, so he does have the B allele. He could have given this B allele. Mom could have given A. So this guy could be the father. If he's the father, of course, he would be BB. Now this man over here, he's type O, so we know he's OO. Okay, he does not have an A or B. He has no A or B allele to give the child, so he cannot be the dad. So we and say, this man cannot be the father, this man could be. All right, let's look at our last example. Okay, let's see. Mom's type O. So once again, if she's type O, you know she's homozygous, so she's got to be OO. If she's homozygous, she had to give an O to her child. That's all she has to give. So her child's type A, so the child's genotype must be AO, right? She gave an O to her child, and the child has an A, didn't get it from his mom, he must have gotten it from his dad. So we have looking for a dad with type A blood, or rather A antigens in his blood. Okay, this man, oh, he's type B blood. Okay, he has no A to give the child, so he's not the dad. Okay, let's look at our second guy. This guy's type O blood. Okay, just like the mother. So we know it's homozygous O, because O is recessive. And note, he does not have an A, so he cannot be the father either. So neither of these men can be the father, so there's some third man out here who's the father, but we don't know his blood type or anything about it. Okay, so once again, illustrates the limitations of blood typing as paternity testing. So it can prove that a man could not be the father, can never prove a man is the father. And when you're working these problems, start out with the child, figure out what the child is, figure out what the mother is, and then find out what the mother gave the child. And then you're looking for the source of that second allele. You don't have to find a dad who has that allele.